It's Mrs. D. I want to go through a couple things just because we're a little short with snow days. So this is more so atomic structure and electron configuration. You've seen this throughout Chem 1. I want to go through the little bits of extra today. And you might hear a little bit of review from Chem 1, but I just so that you can kind of put it all together. So let's take a look. First off, a lot of people get confused when we ask, what is electromagnetic energy? And if you look at the first bullet, it says it's a form of energy that's reflected or emitted from objects in the form of electrical and magnetic waves that can travel through space. So that's where it actually comes from initially, is mainly all of our electromagnetic energy comes from the sun. But then many things within our earth and within the people that live here and the things that are here, we can maintain that electromagnetic energy that the sun gave us in the first place. So if you look at the photo there, it says you have a magnetic field and you have an electrical field. And because of the two, the electromagnetic energy moves in waves. And so you see a wavelength there. And if you look closely, you'll see this sign for a wavelength. We're going to use this in a calculation when I see you guys at school next. So for visible light and other forms of electromagnetic radiation, what we use them for in chemistry is to infer the energies of electrons within atoms and molecules. So we're looking at how those electrons are moving. And if you remember back from atomic history structure, we've talked about Schrodinger, de Broglie, Heisenberg. They kind of all work together in the process that these electrons do move in waves. And they looked at photons also. And if you think about this with our photoelectron spectroscopy, a photon is what is added. It's basically a quantity of light that travels and that can remove electrons. So there's some transfer of energy there. Another dude who is super present with all of this research was Max Planck. And that's where he said this electromagnetic energy is quantized. And that quantized, if you think later down the road, we get the quantum mechanical model. But that means electrons can only exist at specific energy levels and are separated by intervals. So think of that when we get to 1s and 2s and certain energy levels within the subshells, the s, p, d, and f subshell. So with that being said, the shell model of the atom, and this is going back to basically the Bohr model, and the Bohr model did take electromagnetic energy in perspective, but he was limited to only 2 dimensions. And we know that, but it's a great way to explain things, as much as I sort of dislike using the Bohr model. However, the forces between the electrons and the nucleus result in opposite charges, because we know the nucleus has an overall charge of a positive charge, and then the electrons are negatively charged. The nucleus contains those positively charged protons along with the neutrons, but the neutrons have no effect on the charge, and the neutral neutrons, and then we have the electrons obviously surrounding. And let's see how this all affects. Coulomb's law. So this is where we discussed briefly in class, where Coulomb's law, we're not actually plugging in numbers and legit calculating everything. But this Coulomb's law is basically thinking about a force of attraction. And it's basically the law that kind of backs up effective nuclear charge, that backs up shielding. And we'll take a look at that in just a second. So we have a K constant, and that's not really going to have much of an effect right now. But the Q's are the magnitude of charge associated within a particle. So that's basically the number of protons or electrons. And that's where we refer to the effective nuclear charge. As we know, there's more protons in a particular of an element in a particular energy level, then there's going to be a higher effective nuclear charge, meaning there's more of a pull from the nucleus. Now, the d is simply the distance between the charged particles. So then we're thinking about, hey, say how close is a 1s electron compared to that of a 4s electron? That's what we're talking about, the distance between these charged particles, between the protons in the nucleus and the electrons in the electron cloud. So this force of attraction obviously decreases as the distance between the outermost electron and the proton increases. So as the atomic radius increases, this force of attraction between those and the valence electrons, the protons and the valence electrons, is actually decreasing. So again, looking back at the shell model of the atom, we know according to Bohr, there was a two-dimensional set, and they were quantized, meaning that we had a first energy level and a second energy level. And according to Coulomb's law, the forces of attraction between the electrons and the nucleus in N2 are less than the force of attraction between the electrons and the nucleus in N1. And that's simply because the distance is shorter, therefore making the overall attraction force larger. So with inner core and valence electrons, just kind of looking at the difference and just realizing the difference between the two, the inner core electrons are contained in the inner shell. So when we talk about inner core electrons, let's say our valence electron shell is like the third energy level. Well, our inner core electrons would be those of the first and the second energy level. The valence electrons then obviously are contained in the outer shell. So that leads to the shielding effect. So the electrons that are furthest from the nucleus are partly shielded by the inner core electrons. When we say shielded, shielded basically from the pull of the nucleus. So if we take a look at argon here, we see that argon's outermost energy level, argon's outermost energy level actually has less of a pull because there's so much shielding in between the outermost electrons and the nucleus, basically that contains that plus charge that's pulling it. That's what we mean by the shielding effect. We have this electrostatic repulsion from the inner core electrons, and that reduces the electrostatic attraction. So what that means, looking back at this picture, is that when you have more inner core electrons, that electrostatic repulsion, that means when these electrons are too close, they don't want to be close to each other, so they repel. That repulsion keeps even more of those from the valence shell wanting to have that ability to have more of an attraction to the nucleus. So it kind of holds those in place. It holds those valence electrons in place, which is important in bonding. So the first ionization energy, and again, shielding, ionization energy, Coulomb's law, it all comes together. And so the first ionization energy is a minimum amount of energy required to remove an outermost, least tightly held electron from an atom in the gas phase. Now, we do these in the gaseous phase because in a solid phase, it's like not really possible to do this. So whenever we measure this kind of stuff, we're measuring it in the gas phase. So just keep that in mind. We know that some things, iron, is not gas in a normal phase, but if you change the pressures and the temperatures, we can in fact study it in the gaseous phase. So let's take a look at the first ionization energies, and let me raise my face just a little bit so you can see even better. But you can see that helium has the highest ionization energy. Whereas as you go down the alkali metals, so you have hydrogen, lithium, sodium, potassium, you are decreasing in ionization energy because you're increasing in the distance from those valence electrons to the nucleus. What I want to show you, though, in particular, are these little spikes in between. And we're going to take a look at this little spike in between here of sodium and argon. So sodium here is the alkali metal, and in that same row, in the third energy level, you have aluminum. And aluminum, actually, that's where you have kind of like a little spike where it goes down a little bit. Because let's think about the ionization energies looking at the orbital diagrams. You have one electron in the 3p orbital on aluminum. That means that one electron is actually not held super tightly. It's further from the nucleus, and there's a lot of electrostatic forces in between that and the nucleus, and there's not a lot in its own energy level to be held. So that's why the aluminum actually decreases a little bit in ionization energy after it increases in the 2s. If you look down here to sulfur, let's think about sulfur here. Sulfur does have relatively easy access to these electrons, but there are 3 electrons in the outermost shell. So it's going to be a little bit more difficult to grab those. Compared to argon, it's going to be a lot more difficult to grab those because there are so many, and there's that also electrostatic that's just holding these together. Even though there's a repulsion, it holds them in place. So because there's so many, they're going to be more tightly pulled to the nucleus because of the effective nuclear charge. There's more protons, therefore there's a greater pull from the nucleus. Oops. Okay, so first ionization energy, we've seen this before, the trend. Typically, we look at helium, and I would say He has a high IE. So that helps us remember that helium has a high ionization energy, meaning that it's small and those outermost electrons are close to the nucleus. So taking a look then at the actual numbers here, and you can relate it to Coulomb's law. So we have the ionization energy of hydrogen here compared to the ionization energy of helium. The ionization energy of hydrogen is not tiny, and it's because it's so close to the nucleus. But the ionization energy of helium is almost twice that. And that is because we have twice as many protons as hydrogen. Now, I know that means there's 2 protons and 1 proton compared to hydrogen. But when you look at it as a proportion, like for Coulomb's law, then you can see, hey, Coulomb's law can also help us determine ionization energy. Let's take a look at hydrogen versus lithium. So we have hydrogen here versus lithium, and lithium is very much smaller. It's like less than half as large as the ionization energy of hydrogen. And so if we think about it here, the distance is that much greater. So even though the charges are the same, the distance is that much greater. So that is what's making that ionization energy so much lower, because that attraction force isn't nearly as strong. So the shell model of the atom, we have ionization data that suggests electrons then are arranged in shells. And so here we are still, and we like to use the shell model just to help us to understand the Bohr shell model, to help us understand energy levels. We will get to the quantum model here. So again, we look at the outermost energy electrons as they increase. That means the protons are also increasing, therefore increasing the effective nuclear charge. Okay, so let's look at the shell model with the periodic table. So we have the first row of the periodic table has 2 elements, and n equals 1, meaning the first energy level can hold 2 electrons. The second row, the second energy level, can hold 8, and the third energy level can hold at least 8. Particularly if they get into the Ds, it can hold more. So that shows you also as you get further away from the nucleus, the ionization energy also decreases. But that gets us to the quantum mechanical model. And the quantum mechanical model shows us that these electrons actually do not follow these 2-dimensional orbits. Instead, a wave function describes an electron's possible positions, and it's also called an orbital. So I know that's really confusing because we think of an orbital being like Bohr's model, but this is also called an orbital, but it's more of a 3-dimensional orbital. Now, these wave functions include things you already know: 1s, 2s, 3D, 4p, 6p, all of these that you already know. So every electron under one of these labels in an atom is at the same quantized energy level. So what is an orbital actually? And so this is hard to imagine because thinking of this abstractly is actually really difficult, especially when we can't see electrons on a typical basis. So an orbital is a graphic representation of the space the electron will occupy 90% of the time. Those electrons are not going to stay in an s orbital 100% of the time. So these orbitals are concepts. It's not necessarily a physical structure. So let's say this is our 1s sublevel, and that's the location where electrons can be found 100% of the time. But look, there's some outliers around here. Just like, man, Miss D is usually pretty happy, but there's some days where my personality and characteristics of my day might be an outlier. So looking at that, an area where an electron can be found 90% of the time is what we consider an s orbital. And we represent that s orbital by a sphere. So we use a graphic representation to show, hey, where is that electron most of the time? These are p orbitals. So there's 3 of them. This is one p orbital along the x-axis. Here's another p orbital along the y-axis. And here's a third p orbital along the z-axis if you think of something coming out at you. So you have the 3 p orbitals together, and the chances of those being in there is about 90% as well. Now, I don't want to go over this. If you need some more information on electron configuration, you can watch an old video of mine. But just to get back to electron configuration, what I want to show you here is many of you might wonder why. You're like, Ms. D, why didn't it go into the 5D1? Well, there's a reason for that. And so we're going to get to that here in just 1 second. This also we may see as a little bit differently too. So let's take a look at what D's and F's actually do sometimes. So first off, with electron configuration, we've done this in Chem 1, is electron configuration of ions. So we know that if we have a plus charge, that means we have one more proton than we have electrons. So therefore we lost an electron. So therefore Na plus is actually more stable than sodium itself. And so that's really what they're actually trying to seek, is that stability. So they want to acquire that electron configuration of a noble gas. Another thing that would be helpful, and I know we've talked about this in last semester, but isoelectronic species, and you guys need to know this terminology. Isoelectronic species, they share the same electron configurations, but they have a different radii. And the reason why they have a different radii is because we have different number of protons in the nucleus. So if we have more protons, for example, the nucleus pulls tighter on the electron. So the atomic radii may be smaller. So that's where we looked at ionic radii last semester. So if you look at argon, chlorine, sulfur, calcium, and potassium, actually calcium has the greatest number of protons. So that would be actually the smallest of all of these. Now, D block cations. This one's kind of weird, and I'm not sure that you guys have realized this yet. But sometimes these elements lose electrons from their highest S sublevel before losing them from their D sublevel. And this is where those Ds are stronger. So think of it this way. According to the Aufbau principle, the D electrons have a higher energy than the S electrons. So therefore, the Ds are actually capable of stealing the S electrons and putting them into the D electrons. So in this case, we're looking at it in terms of iron and the ions that the iron holds, is that many times if iron loses 2 electrons, those 2 electrons are typically not coming out of the D. Instead, they would be coming out of the S, the 4s orbital. First of all, these are lower energy levels. And if you think about it, 4s, that's going to be easier to access because they're in the 4th energy level. Notice here, if we have a 3 plus charge, 3 plus cation and an ion, we're going to lose 3 electrons from 2 from 4s and 1 from 3d. But notice we're going to lose them from the 4s first. We're not taking 2 from the 3d. So when we go to rules for filling orbitals, and this is just a reminder because we've done this last semester with orbital diagrams, where we have to remember these 3 rules. First of all, the lowest energy levels are filled first before filling the higher energy levels. And that's where, just think of it as building a skyscraper. You have to build the bottom level before you can build the top. But the top, whoever's at the top, pays a little bit more money than those people who are paying at the bottom. The Pauli exclusion principle, each orbital can hold a maximum of 2 electrons that spin in opposite directions. One spins clockwise, one spins counterclockwise, and it's because there's 2 electrons and they're both the same charge, and so they want to repel. And finally, we have Hund's rule when there's more than one orbital in a subshell. So if we're talking S, P, D, and F, a single electron is added to each orbital before adding a second electron to the orbital. So you may remember me describing to you guys that Mama would feed all of her Huns first before anyone got seconds. And so we look at that as per orbital and subshell. So that means like in a 2p, for example, we're going to put 1 electron in each 2p orbital before we put a second electron in any of those. So an orbital diagram, if you forget what an orbital diagram is, you're going to find that these come up a whole lot more in AP chemistry than they did in Chem 1. So you notice here, we're following Pauli exclusion principle by putting the electrons going in opposite directions. We're following off-ball by filling the 1s orbital before we fill the 2s orbital. Hund's rule is really not applied here. But if you look at fluorine, Hund's rule is applied here as well as the other rules. So you see Hund's rule is applied here in that we have basically 3 orbitals in the subshell of 2p. So we would fill in the electrons 1, 2, 3, and then we would fill in 4 and 5. So we don't fill that in like all at once. This would be incorrect because it's not following Hund's rule. This is correct because we are following Hund's rule. It does create a lower energy system, which actually keeps those electrons closer to where we need them to. So just to wrap up some terminology here, sometimes it's hard to know when to use subshells, when to use orbitals, all that good stuff. So N equals 1. N is energy level, and the energy level 1 contains 1 subshell, which is a 1s. That 1s subshell can hold 2 electrons total. A second energy level, N equals 2, contains 2 subshells, 2s and 2p. A 2s subshell can hold a maximum of 2 electrons. A 2p subshell can hold a maximum of 6 electrons. So I want you guys to try to get the idea of that terminology. And finally here, just with 4D, and so if all of these were filled, and you're like, hey, if it's possible, how many electrons would be in the 4th energy level? Then you would add all of those electrons together, and it's actually possible for there to be 32 electrons in the 4th energy level if these were all filled. Finally, we look at shielding effect within a shell, and you see these graphs. You don't have to go all out trying to figure out how this works and everything. You just need to see that as the distance from the nucleus increases, the probability of where those electrons will be it changes a little bit. And so in general, the more effectively the electrons within a subshell are able to penetrate the shielding electrons, the greater the ionization energy of those electrons. So that means then the more effectively the electrons within a subshell, so let's say they're in the 3D subshell, they're able to penetrate the shielding electrons, making it a higher ionization energy, making it more difficult and requiring more energy for those electrons to be removed from the inner parts. Okay, so I know it's a little confusing putting all of this together, but you guys are doing great. And there's just a few little things throughout, and we will work harder tomorrow so that we're ready for our test. Take care, guys. Bye-bye.